Hello everyone. In this video, we are going to learn about sinusoidal response of RLC series circuit. So as you can see, we have RLC series combination. So this was excited by the sinusoidal voltage V of t. Let us say this as V cos omega t plus theta through a switch S. The switch was closed at t equal to 0. And we need to assume that initially the inductor and capacitor both were uncharged. Okay, so this is the initial guess. Okay, so initial guess that inductor and capacitor both were uncharged. That means the current through the inductor is 0 and voltage across the capacitor is 0. Okay, so these are the conditions for inductor and capacitor. When switch was closed at t equal to 0, we can apply KVL because we can observe a closed path if the switch was closed. So now I'm writing the KVL equation now. So voltage across resistor plus voltage across inductor plus voltage across capacitor should be equal to supply voltage V of t. As we already know, VR is R into I plus voltage across the inductor L into di by dt plus voltage across the capacitor 1 by C integral I into dt, which is equal to what is V of t? That is V cos omega t plus theta. So where is this I? So this I is nothing but our loop current. Okay, so I already told you in the previous videos that I is nothing but I of t. So I always chose I instead of I of t. Okay, so it is only for our convenience. Okay, so if you want to write I of t, you may write, no problem. Okay, so now I don't want the integral now. Then what I should do? So I have to differentiate this equation with respect to t. So there we get r into, as the current I is function of time t, so we can write d by dt plus L into d square I by dt square plus 1 by c into differential of integral of I dt will be I only, which is equal to V. So for cos, you're having minus sine omega t plus theta. Again, for this portion, the differentiation is omega. I'm writing this omega here. Okay, so this is our differential equation. Now what I'm doing, I'm dividing this entire equation with L so that I can get the second order differential equation. So if I do so, I'm writing this term first. So what I can get, d square I by dt square plus, so take this as a second term, then it will be r by L into di by dt plus, next take this term, that is 1 by LC into I is equal to minus V omega by L sine omega t plus theta. Okay, so we may also consider this equation as, so d by dt may be considered as capital D. If we do so, then suppose let us say this as equation 1. Okay, so how we can write the equation 1 now? So this is d square plus r by L into d. Okay, so this is L. Okay, r by L into d plus 1 by LC of I is equal to minus V, it's not small v, capital V, V omega by L sine omega t plus theta. Like this we can write. So if you want. Otherwise, you can call this as directly equation 1. Okay, so now let us see how what is the solution of this particular equation. So what could be the equation, what could be the solution for this equation? Obviously the current I. Okay, so let us see how the solution can be found. Okay, so the solution for the current I will be having two parts. The first part is a complementary function and the second part is a particular solution. So first I'm doing the particular solution, later we'll come to complementary function. So in order to find the particular solution for this differential equation, let us assume IP, that is particular solution. So let IP stands for particular solution, equal to A cos omega t plus theta plus B sine omega t plus theta. Okay, so later we are going to use the differential part and the second derivative of this current expression. So that's why here I'm taking dip by dt. Let us say this as ip prime. So I'm doing directly here. So this derivative part, so for cos, the derivative is minus sign. So minus a omega sine omega t plus theta plus b omega cos omega t plus theta. So this is the first derivative. So if you want, you can call it as equation 2 and this one as equation 3. Now, so take this other derivative also here. So double derivative, that is d square ip by dt square equal to, let us call it as ip double prime. So do the derivative for third equation. So there you get minus a omega cos omega t plus theta plus b omega square. It's not plus b, but you get minus, so keep minus here because for the cos derivative is minus sign. So minus sine omega t plus theta. So call it as equation 4. Okay, so now you did you remember that equation 1, Roman 1? Okay, so what was that equation 1? That is d square I by dt square plus what was that? D square I by dt square plus r by l, right? So this is r by l into di by dt plus 1 by lc into I is equal to minus v omega by l sine omega t plus theta. So this is our equation, right? So in this equation, instead of I, you take IP. There you get the particular solution. So if we substitute, then what we can get? So let us call this equation as normal equation number 1. So please correct in the previous slide also. So now from the first equation, what we can write? So first term, what is that? D square IP. Instead of I, read IP. So there is nothing but equation 4 you may substitute. So this is minus a omega cos omega t plus theta minus b omega square sine omega t plus theta. So this is d square ip by dt square plus r by l into di by dt. So di by dt means equation 3, that is minus a omega sine omega t plus theta plus b omega cos omega t plus theta. Okay, so the second part is over. Now go for the third part. What is the third part? Plus 1 by lc into I. What is I? I is nothing but ip, that is a cos omega t plus theta plus b sine omega t plus theta. Okay, so which is equal to, so third part is over. So what is the other part over the other side of the equation? That is minus v omega by l sine omega t plus theta. Okay, so now what we can do now, on the LHS side, okay, on this side you just separate sine and cos terms. If we separate, what we can get? So let us see.
So we will be getting minus a omega square plus b omega r by l plus a by lc. This is cos coefficient, that is cos omega t plus theta. Okay, now what is the sine coefficient? That is minus b omega square minus a omega r by l plus b by lc into sine omega t plus theta equal to minus v omega by l sine omega t plus theta. Okay, so now what we can do? So we can compare on both sides. So if we can compare, then we may write minus a omega square plus b omega r by l plus a by LC. So is there any cos coefficient on the other side? No. So keep 0. Let me call it as equation X. Okay, so now you compare the sine terms. Then what you are getting? Minus B omega square minus A omega R by L plus B by LC is equal to minus V omega by L. Okay, so call it as equation 1. So we got two equations. So this equation can be even more simplified, like take A as common now. There you get 1 by LC. First write 1 by LC, this portion. Okay, next minus omega square plus B into omega R by L equal to 0. So you may call this one as equation X. Okay, not 1x. Now this equation is also can be modified. So take A out. Okay, so you got minus here. So minus A into omega R by L. So take B out as common. There you get 1 by LC minus omega square is equal to minus V omega by L. Okay, so if I want to exclude that negative sign for A, you may. There you can get multiply the entire equation with minus. There you get A into omega R by L plus B into, you may write it as omega square minus 1 by LC is equal to V omega by L. Okay, you may call this as equation 1. So after solving these two equations, we will be getting the relations for A and B. So I'm writing the direct relation here. So A will be V into omega square R by L square by omega R by L whole square minus omega square minus 1 by LC whole square. Okay, so this is A expression. Okay, so V omega square R by L square by omega R by L whole square minus omega square minus 1 by LC square. Okay, now the B expression will be, okay, so this is omega square minus 1 by LC, okay, 1 by LC into V omega by L into omega R by L whole square minus omega square minus 1 by LC square. Okay, so this is how we will be getting the relations for A and B. Now, can we write the relation for IP, the particular solution? That is what A cos omega t plus B sin omega t. So instead of A, you write this expression, okay, cos omega t plus theta plus B. So you write this expression B sin omega t plus theta. So in this way we can find IP. But the IP expression will be lengthy, you know. So in order to have in a compact size of IP, so we will be assuming this A and B with M cos phi and M sin phi. Let us see how that can be done.
Okay, so letting or putting M cos phi. So M cos phi as, what is the first portion? So this is V into omega square R by L square divided by omega R by L whole square. This is not plus but is of minus. Okay, so minus omega square minus 1 by LC square. Okay, so this is our M cos phi. Now what is M sin phi? I will write here M sin phi as V of omega square minus 1 by LC into omega by L into omega R by L whole square minus omega square minus 1 by LC square. Okay, so these are the expressions for m cos phi and m sin phi. Okay, so now it is the time to calculate m and phi. So how do you calculate m and phi? Let us solve this as equation A. So this as equation B. Now what we can do? So do like this: a square plus b square. So then what you get? So this is m square cos square phi plus m square sin square phi. So do the calculation. So we will be getting the expression for m. Okay, so I'll be writing directly here. So there you get v square by, it's a simple calculation. Okay, so r square plus 1 by omega c minus omega L square. Okay, so this is all. Can we take m as out? So s we may take. So m square, what is cos square phi plus sin square phi? Nothing but 1. So instead of this portion, okay, so this cos square phi plus sin square phi, we can have 1. So there you get m square as v square by r square plus 1 by omega c minus omega L square. Okay, so I want m. So then what I should do now? So square it on both sides. So there you get v by root of r square plus 1 by omega c minus omega L square. Okay, in this way we can find m value. Now it is the time to calculate phi. How you calculate phi? So then obviously you do m sin phi, that is equation B, divided by equation A, that is m cos phi. Okay, so m gets cancelled. Okay, so we'll see. So if you solve, then I'm directly writing here. Okay, so after the calculation, so it will be omega L minus 1 by omega C divided by R you'll be getting. Okay, so now it will be tan phi. So tan phi is omega L minus 1 by omega C divided by R. If I want the expression for phi, then what I should do? So tan inverse on both sides. There you get tan inverse of omega L minus 1 by omega C by R. In this way, we can find m and phi values. Now, finally, what we can write for IP? So, IP can be written as m. What is m? This v by root of r square plus, is that not xc? Okay, so xc minus xl square, okay, into cos omega t plus theta plus tan inverse of omega c 1 by omega c. You may write it as xc also. Okay, L by R. Okay, in this way we can find the particular solution. Now we'll solve how the complementary function can be solved. Okay, see, the complementary function is similar to that of DC series RLC circuit. So if you want the reference, I'll be giving that reference in my description box. You can please verify. Okay, so to find the complementary function, we have the characteristic equation. No, what is the characteristic equation? So what I told you, so you can have d square by dt as d. So and sorry, d square and d by dt as d. So like that you can imagine. No, so if you imagine, so that equation 1 can be written as, okay, so keep this in mind. So that equation can be written as d square plus r by l into d plus 1 by lc of I equal to 0. Okay, so actually this is the equation where you can observe in DC RLC series circuit. Okay, so here the characteristic equation is nothing but this one. So that means d square plus r by l into d plus 1 by LC equal to 0. So this equation is called the characteristic equation, and this was discussed in our DC excitation RLC series. Okay, so this is like, you know, what kind of equation? Ax square plus bx plus c equal to 0. So this kind of equation, no. So for such kind of equations, what are the roots? Roots are minus b plus r minus root of b square minus 4ac by 2a. So using this formula, we are going to solve the roots for this particular equation. So let us see. So the roots, let it be d1 comma d2 is equal to minus b. So what is b here? What is a here? You compare these two equations. What is a? A is 1. What is b? B is r by l. And what is c? C is 1 by lc. Okay, so these are the ABC values. Okay, so now let us go with the roots. Minus b, so that is minus r by l minus b plus r minus root of b square. What is b square? B square is r by l, b square, r by l square, b square minus 4, a value 1, c value 1 by lc, okay, by 2a. Now, if you solve, you'll be getting minus r by, what is a value? A value is 1. So, this is nothing but our 2. Okay, so r by 2l. So, divide this 2 with each and every element. So, there you get. So, if you take the 2 into the root, you'll be getting 4. So, you may write this one as r by 2l whole square minus 4 gets cancelled. You'll be getting 1 by lc. Okay, so these are the roots d1 and d2. Okay, so here let us assume this part as k1 and this part as k2. So it is very clear that k1 is a negative value. What about k2? So k2 is a root value. So k2 can be, we have the probabilities, k2 can be positive value, k2 can be negative value, or it can be 0. So you're having three cases, three different cases. So depending on the k2 value, your complementary function is going to be varied. Okay, so let us see for all the three cases. Okay, so first let us assume that k2 becomes positive if k2 becomes positive. So what is k2 actually? So k2 is root of r by 2l whole square minus 1 by LC. When this K2 will become positive, that means R by 2L whole square is greater than 1 by LC. If this condition is happening, then we may say K2 is positive. So if this K2 is positive, so how the roots will be? The roots will be real, unequal. Okay, real, unequal, and under this condition we can expect overdamped response. Okay, overdamped response we may get. Okay, so the explanation is there in the previous video, so please refer. So for such kind of conditions, then the equation looks like d minus, let us say the first root k1 plus k2, okay, into next d minus k1 minus k2, okay, so other part into I equal to 0. Okay, so for such kind of differential equations, the complementary solution will be IC equal to C1 into e power k1 plus k2 into t plus C2 into e power k1 plus k2 into t. Okay, so this is the complementary solution. Now, what could be the complete solution? The complete solution is complementary function plus particular integral. So there you can substitute C1 into e power k1 plus k2 into t, your entire expression C2 into e power k1 plus k2 into t, and you call back the expression for IP. I'm not writing here. Still this I is incomplete because you are having C1 and C2 values. So how you calculate C1, C2 values? Using initial conditions. Using initial conditions, you may calculate C1 and C2 values. Once you solve C1, C2, substitute here right in this equation. So you get the complete equations or complete solution for the current I. So this is first case. Let us say this as case 1. Okay, so now what is the case 2? Case 2 can be if K2 becomes negative. When the K2 will becomes negative, that means R by 2L whole square is less than 1 by LC. If this happens, then we may say that K2 is a negative value. Okay, so under this circumstances, how the roots can be? So how the roots can be? The roots are complex conjugate. I'll be writing here. So the roots are complex conjugate. Okay, which gives what kind of response? Which will gives underdamped response. Okay, underdamped response you may expect. Okay, so now under this particular conditions, how the equation can be written? So the equation can be written as, okay, so this is d minus the, what is the first root? K1 plus jk2. Okay, first part is over, and the second part is d minus k1 minus j k2 into I equal to 0. So for such kind of differential equations, the solution, the complementary solution will be e power k1 into t into c1 cos k2t plus c2 sin k2t. Okay, so now as usual, in order to have the complete solution for the current, if the case is under case 2, there you get IC plus IP. Now you substitute the IC expression with this, and IP just we solved in the previous slide, so please add the expression here, so you get the current I. So with IP we don't find any difficulty because we don't find any constants, but in the complementary solution you're having C1 and C2. So those values, how we solve? Again using initial conditions. Okay, again using initial conditions we may calculate C1 and C2 values. Okay, so this is how we can get the complete solution for the current I if K2 is negative. So what could be the other case, final case, that is K2 0. Let us see the case 3. Okay, so now case 3. So what is case 3? K2 becomes 0. When this K2 becomes 0? When R by 2L whole square is equal to 1 by LC. Then we may say the K2 is 0. Okay, so then what happens with the roots? The roots which are gives so what kind of the roots are simply only K1 because K2 is 0. So that's why you'll be having only K1. So the response will be critically damped response you may get. Okay, so critically damped response. Okay, so this is a critically damped response case. Now how the equation can be written as d minus k1 because k2 is 0. Okay, next d minus k2 into I equal to 0. Now what is the complementary solution for such kind of differential equations? We know very well that is e power k1 into t into c1 plus c2 into t. Now what is the complete solution for the current I? That is I plus IP. Okay, so now you substitute IC here and you also substitute for IP, then you get the complete solution. But still C1, C2, these are unknowns. So those values can be found using initial conditions. Okay, so in this way we can find the complete solution for the current I for RLC series circuit with sinusoidal excitation. I hope this video is helpful for you. So if you find any helpful kind of thing in this video, so please do share and support our channel. Thank you so much for watching this video.